Hello everybody and welcome to today's video. Here we're going to talk about the difference in this particular case between switch case and a virtual table. And those are the kind of questions that usually come to one's mind is what is faster? What is more efficient? And thus, what should I actually use if one is more efficient than the other? So, those are the kind of questions that are, I guess, the backbone of software engineering and computer science. If an algorithm is faster than the other, we are going to use the faster one all day, every day. So, I've and in this video we're not going to use like compiler explorer because we will be benchmarking our code with perform Linux compile command line tool, and here we're going to call sudo prefer stat to generate the stats that we need in order to evaluate the number of CPU instructions and the percentage of the backend bound and the front-end bound. So if you haven't heard about the backend bound and front-end bound, the difference is essentially front-end bound is when there's no work done and the program is yet to execute your instructions, whereas so it's trying to read the instructions and then execute them. But backend bound is when we jump straight to the point of executing the instructions. So it's like cutting to the chase. So let me just move this out of the way and show you my code. So my use case would be to have a value class, and this is really common in languages that tend to be dynamically typed, is that particularly we have a union wrapped up in a class. Or if you want to have a value that has multiple types, you would implement an enumeration and the union to match with that enumeration values, with those enumeration values. So what I did here is pretty typical. I will actually show you what I'm talking about here. So C++ union. So it is pretty common that you have something called union-like classes. A union-like class is either a union or a class that has anonymous type. So the reason that you need to have an associated type to your union is that you can keep track of the active member in a nutshell. So I also sort of Googled for, when should you use a switch case as opposed to a virtual table. And here it says it's generally faster, but it really depends on the use case. So I picked a use case where we can time the difference, where we can time the performance and compare. So it's all pretty straightforward stuff. We have a union, can be a number, character, or a string, and then we essentially need to invoke the destructor. let's say each time we're trying to use our value, we will effectively need to implement or have our CPU execute the jump instruction, and that will be the indirect jump of the switch case table. Also, I also made sure that in a switch case table there is an built-in unreachable compiler extension, and this is GCC specific, so that we remove the compare overhead of our jump table. We talk about this in much greater detail in the blog called Source Compilers Understanding Switch Case Statements, as well as switch case peak performance, or trying to achieve a peak performance. So we get back to my code. So essentially, we've, like I said, anytime there is an operation, a switch case or jump table is something that our CPU needs to execute. And I've written a pretty straightforward benchmark here where we essentially call it in a very, very expensive loop, and we time the difference. So just to cut to the chase and say, why is switch case typically faster in this scenario as compared to a virtual table? Well, it is so given that the compiler can inline your functions, and with a switch case and with a virtual table needs to be evaluated at runtime, so there is no, and you have to make a function call, so that you make a function call, you make a push onto the stack, pop onto the stack, and actually before that return the value and pop off the stack. So that is actually three possibly very expensive operations compared to something that you can inline and use a switch case. So if we time this result, we're not going to time it just yet. I'll just now show you the code that I've implemented myself without using the virtual keyword of C++. Now, many of you might be like, oh, hey, okay, this is way too complicated. It is, but what's the upside of this is you're controlling your code. Whereas I know that C++ keyword, virtual keyword has so many built-in things to it, other than just the keyword itself, such as like dynamic cast and stuff like that. So, and it's usually better to implement your own virtual table if you are trying to, improve your knowledge or your experience in C++ or even C. Because see right here, this code, you can port it into C. And you cannot port virtual keywords into C because they are C++ specific. It's not going to be effectively a copy and paste. So that brings me to the point, what are we doing when we are creating a virtual table? We have And I have a little diagram here. Usually, and the reason why you see an additional 8 bytes to your class where the keyword virtual is used is because it is trying to point the virtual table within the set struct slash class in C++. This is because it needs to control each instance, each and every single instance. Otherwise, it wouldn't be able to make decisions. So if you're replacing switch cases, for example, switch case needs to determine, okay, what's the type of my enumeration, so I can understand what can I do, what I'm doing actually. So if you see a left and right, so this is essentially a plus. And when we say 1 plus 1, we're saying plus 1, and once we 1, call a function here. And then we have to determine, okay, is left a number? And is right a number? If so, we return. We're not going to use the if statement there, even though I used the if word there. And the point is, we have to make a decision based on our type. So that's how virtual table essentially works. It assigns a virtual table, a pointer, to the virtual table, because you wouldn't see something like this. This is really, really bad, because now I'm taking the size and the alignment of my of the union handler, and once I keep adding the functions that I need to be overwritten by a virtual table per instance, per object instance, my class size is going to increase automatically, and my code is going to be a nightmare. And its performance, of course, because it will need more memory if you're, I don't know, adding it onto the vector or anything like, or working with it in any other way. So what I created here is a handler string table, virtual table, where if my value is a string, I will have a plus string handler that looks something like this. This is really an alias, right? Because I'm taking the right and I'm going plus, so I will essentially call this at the end. Where I'm computing the two. And I'm 100% sure that both left and right will be a string. We can add a logic here that says, oh, you can't do that if it's not a string. But that's some additional validation that we can do. And that can be a problem, because that's not a problem with switch case, right? Switch case already determines what's our type. And you can easily jump to the case where I cannot compute, let's say, a string with a number. Whereas here we need to write an additional if statement, which is compare and a conditional jump, and then the function call. So, and the reason these things, I mean, a virtual table is not optimized is that you cannot inline a function pointer. As you can see here, we are assigning a virtual table here, and we have function like a struct of function pointers. And when you have a struct of function pointers, well, goodbye inlining. So we essentially And I got inspiration for this, or actually I didn't. I was coming up with this concept on my own, and I called it union handler. But then later on, I realized, well, this is just another virtual table, isn't it? And I was trying to understand the actual implementation of a virtual table. And the only public sort of piece of information I could find is in a book called Understanding and Using C Pointers. This book, this is probably the only book where I could find polymorphism associated with the C programming language. And they are essentially creating a base class that's called shape, and they create they define rectangle, and so they have rectangle and a square, I believe. Is it a square? Yeah, well, you can create squares based on it. That's that's the main point. So they create a base, which we essentially do in our code there, but we don't have a direct base. It's just a virtual table, right? Because our use case here is not to cast from the base object to the derived object or the other way around. Is just wrapping it inside of a union class, and that's entirely other use case. It's not exactly polymorphism per se, but we're still using the virtual table, right? So they say here that this is typically achieved by a virtual table. The only problem with this code here is that they are using, and we just pointed out, they're using a struct directly that is aligned and direct size of the v functions. And the v functions, as you add up more functions, will increase the size of your object. And that's extremely bad. So you want to make sure, because these are the kind of things that can be defined at the global level in our code, right? Because they're just pointers, right? And there will be no problem with that whatsoever. So this is probably the only improvement I would make here. This is a pointer, because essentially that's how C++ treats it, using the virtual keyword. Otherwise, it would be a nightmare. So you can see here that in my value class, I'm calling the destroy, and this destroy really depends on my virtual table. And these handlers when I'm destroying a number, there's nothing to destroy. It's a primitive, right? But when I'm destroying a string, I need to explicitly call or invoke the destructor, because unions in C++, as we covered in our first video, they need their destructors invoked explicitly. So that's essentially our idea of this code here, and I will make sure to post it on GitHub and share it with you so you can break it down at your own pace. So let's get to the actual benchmarking of this code. These two C++ programs. So when I benchmark my switch case and I take a look at the number of core, and the important stat here for us is the number of core CPU instructions and the instructions per cycle. We can see here that the instructions per cycle for a virtual table is, well, an implementation of it is 3.7, and this is 2.7. Now that's a big jump, and this is about 42 billion, and this is 15 billion. So we are like 100%. We're using 100% less operation, or not actually. Well, about I don't know, 150%. It's as twice. It's this one is as twice as this one, almost. But yeah, this would be 32 if multiplied by 2. So it's about 130, 140% easy. So that is so much faster for this use case. So I would never use a virtual table in a case of my union class. And you can see it online in many samples and examples of various C++ code that nobody really uses a virtual table for a union class, and that would be the point. And another important stat for us here is backend and front-end bound. So we're seeing that the CPU here actually does the work. There's no front-end bound really, it's negligible really. It's 5%, 3%, and the backend bound is 58%, whereas for the implementation of the virtual table, backend bound is almost non-existent, whereas for front-end bound, the program is trying to read what to do. There's no actual work done. So I will leave the decision to you whether you want to use a switch case, virtual table, or implement your own virtual table to you entirely. I hope this video was helpful, and yeah, hopefully I help you make that decision. We covered really one specific use case, but it is something worth mentioning and worth seeing. Thank you for watching, and till next time, I'll see you. Bye bye.